Good morning or good day everyone from wherever you are. Welcome back to another video of Che 101, which is actually a project organized by the Academic Committee of the Chemical Engineering Society. Today we'll be discussing a topic under Organic Chemistry 1, and today we'll be discussing a topic that is typically discussed at the latter part of the term. So essentially we'll be discussing how to predict what product will be formed given a certain condition, and that involves us choosing whether an SN1, SN2, E1, or E2 reaction will occur. So, what makes this interesting is after this topic, you should be able to relatively predict what major product you would get given two reactants, or even better, given a product, how can you get that product? So what reactants do you need? What condition would allow you to get that particular product, and etc. To introduce myself, my name is Eliza Tan. I'm currently taking BSMS Chemical Engineering in DLSU, and my email address is added there, so in case you have any questions, you may feel free to message me in email and I'll do my best to respond to them. So what will we be discussing for today? It's expected that at this stage, you're already familiar with the individual mechanisms. So you're familiar with how SN2 works, how SN1 works, E1 and E2 reactions. Because we'll not be going in depth into that anymore, but rather we'll just be giving you an overview of what takes place in these particular mechanisms. Afterwards, we'll be delving into how to predict what major product would occur given a condition. So given this particular reactant, given this type of alkyl halide, what mechanism is most likely to take place and what product are you most likely to get? And we'll also be going through some exercises so you can practice whatever you've learned in this session and identify your strengths and weaknesses. With that, let's start with our first reaction for today, which is the substitution nucleophilic bimolecular or SN2 reaction. And if there's one thing that I'd associate this, I'd say I'd like to think of a ninja. So why ninja? Let's say we have this reaction, the nucleophile and your substrate, which is this one. The nucleophile being negative, it likes to give off its electrons or donate it. And in the substrate, the central carbon is more positively charged because its electrons are being pulled by the more electronegative atoms in that molecule, namely the halogens. So what happens is that the nucleophile is attracted to the more positive part and it will go there. And as a result, the alkyl halide or the halogen rather would be leaving the group. So as a result, you get this NH. Do take note that inversion of configuration takes place, meaning the molecule at the back, found at the back of the molecule, in this case the hydrogen, is now found at the front of the molecule in the product, and the nucleophile is now replacing the position of the hydrogen. So that's what we call the inversion of configuration. And if you want to know why that occurs, you can look through the Johnny Smith and the Solomon, because that's not the focus of our topic for today. And if you notice a backside attack occurs, that's why I call it a ninja. The nucleophile would backside attack the substrate. So these are the properties of an SN2 reaction. We already discussed the backside attack and the inversion of configuration. Concerted reaction means the reaction occurs in one step. So the attack of the nucleophile and the leaving of the halogen or the bromide ion occurs in one step. Second order kinetics means that the substrate and the nucleophile both affect the reaction rate. So why is this the case? The greater the substrate, the number of substrate or the concentration of the substrate, the more likely it is to attack or interact or collide with the nucleophile, forming the reaction. Likewise, if there's more nucleophile, it's more likely to be able to collide with the substrate, and because of that, it increases the reaction rate. That's why it's dependent on both the nucleophile and the substrate. Lastly, this is very important, SN2 reaction is favored by primary alkyl halide. So why is this the case? Well, let's say we have this tertiary alkyl halide and a primary alkyl halide. So let's say we also have our nucleophile, and the nucleophile would like to attack the positive part of the molecule or the substrate, which is the carbon. And let's say the R groups, let's say those are very long carbon chain. So which molecule would the nucleophile be able to reach better? Well, in this case, of course, it's this, because the hydrogen is smaller than any R group. So it'd be able to attack or reach the central carbon better. And we'd say that this molecule, the primary alkyl halide, is less sterically hindered. And that's why it's favored by SN2 reactions. So the gist is, the reaction is more likely to occur if the nucleophile is able to donate its electron to the central carbon. So next, the substitution nucleophilic unimolecular reaction, or SN1 mechanism. I'd like to see this as the social butterfly. Essentially because even if a living group leaves that particular molecule, it's able to attract other molecules to interact with it. So let's say we have this example. That's a tertiary alkyl halide. So instead of the nucleophile being able to attack the central carbon, because as mentioned earlier, it's sterically hindered, meaning the nucleophile is not able to reach the central carbon easily, what happens first is that the molecule decides to remove the halide or the halogen, which gives us a carbocation. And this carbocation is positively charged and it's not as stable. So it wants to achieve its stability by attracting the nucleophile. And since the nucleophile likes to donate its electrons, it does that. And you'd get this reaction. This product. Do note that no inversion occurs, so it doesn't matter whether you get that or this. What matters is that the nucleophile is able to donate its electrons so that central carbon is able to achieve octet rule. Also to take into consideration is this is a two-step mechanism. The first mechanism is the leaving group leaving the molecule, and the second is the nucleophile attacking the central carbon or the carbocation. These are the properties of SN1. It's two-step mechanism. First order kinetics, meaning it's only dependent on the alkyl halide or the substrate. So why is this the case? The reaction cannot occur without the leaving group leaving the substrate. So no matter how much nucleophile you have, it won't matter because it will not be able to reach the central carbon anyway unless the substrate removes its halogen and form a carbocation. So in short, the reaction rate is only affected by the substrate. Lastly, it's favored by tertiary alkyl halide. So why is this the case? Well, let's say we have this carbocation versus this. Both of these carbocations are not as stable as if the central carbon achieved its octet rule or has 8 electrons shared. So in this case, the tertiary alkyl halide is more stable because these have more electrons, so it's able to relatively provide more electrons to the central carbon to stabilize this charge compared to if only hydrogen was connected to the carbon. So because it's more stable, it's more likely to retain, and that's why SN1 reactions prefer tertiary alkyl halides. So next, bimolecular elimination. This is interesting because I'd like to say this is similar to a tug of war. So what essentially happens is that the nucleophile would want to attack what we call a beta hydrogen, and because of that, it causes another atom to leave, namely the leaving group, or rather the halogen. Let's say we have this molecule and we have a strong base. This base would attack the beta hydrogen. So if this is your alpha carbon, this is your beta carbon. So it will attack this. And what happens is that the shared electron would go here, and because this carbon, the alpha carbon, is already gonna have more electrons than it should, it lets go of its halogen. So the bromide ion leaves the substrate, and you end up with this product. An alkene becomes your product. Alkene because there's a double bond. So properties of bimolecular elimination involves, number one, it's concerted. So both the attack of the beta hydrogen and the leaving of the bromide ion or the halogen occurs in one step. Second order kinetics, the reaction rate is affected by both the substrate and the nucleophile. Third, you form alkene if an elimination occurs, typically. And then, attack of the anti-periplanar hydrogen, we'll be discussing that later. And lastly, the side-step rule is followed. So essentially what this means is that the molecule would want to achieve more stability. So it wants an alkene that's more substituted. So let's say we have this product as one option, and then the other option is something like this. So in this case, the side-step rule would state that this product would be preferred because it's more substituted. Anti-side-step for bulky base, of course, that's an exception because the bulky base would just cause the molecule to become more sterically hindered. So it's more likely to want to attack the part of the molecule that's less sterically hindered. So anti-periplanar attack hydrogen is essentially this. So let's say I drew the diagram in advance, but essentially it wants to attack the hydrogen that's periplanar to the halogen. So if this is the halogen, it wants to attack the periplanar. So 180 degrees. Why? Because it's farthest from the halogen, so it's more likely to reach that particular hydrogen to prevent steric hindrance. And then electron would form a double bond, and then that would cause, for this to achieve octet, it will cause the Cl to leave. So next, unimolecular elimination. You can just think of this as E2 with an extra step. The only difference is that, like SN1, the leaving group leaves first before the attack of the nucleophile happens. It's first order kinetic. The reaction rate is affected by the substrate. And lastly, again, it's typically involved in the formation of alkenes. So now, let's move on to the bulk of our discussion for today, which is predicting major products. So there are 4 questions that you have to consider in predicting the major products. Number 1, what kind of alkyl halide is your substrate? Second, is there heating? Third, are you reacting with a strong base / nucleophile? Or lastly, are you reacting with a bulky base? So what happens? What kind of alkyl halide is your substrate? And is it an alkyl halide in the first place? Because if it's not an alkyl halide, then no reaction. So let's say first we have the primary alkyl halide. As mentioned earlier, primary alkyl halide prefers SN2 or E2 reactions. So you only have 2 options in this case, or SN2 or E2. And then our next question, are you reacting with a strong base or nucleophile? If yes, which most likely is the case, you will go with an SN2 reaction. If it's a bulky base, you'd want to have an elimination reaction. The second part of this is there heating? Because normally if it's heating, usually what happens is that an elimination reaction occurs. So just take that into consideration. But again, if it's primary alkyl halide, your only 2 options are SN2 and E2 reactions. If it's bulky, go straight with elimination. If it's not bulky, it's most likely SN2. So next, secondary alkyl halides. Now you have 4 reactions to consider: SN2, SN1, E1, and E2. So firstly, you'd want to ask, are you reacting with a strong base or nucleophile? So let's say strong base meaning OH, OR. No. If yes, then you're more likely gonna be dealing with E2 or SN2. Other sources may say that if it's protic, protic base, meaning it likes to give you one hydrogen, you're more likely going to get a um, you're more likely gonna go with SN1 or E1 because you're gonna have a polar protic environment. But at least in our case, when it was discussed to us, a strong base constitutes two SN2 or E2 reactions as our major product. And if it's a bulky base, you'll get an SN E2 reaction. If it's a weak base, we'll go through with E1 or SN1 reaction. For SN2 versus E2 reaction, at least, you can just say that both will give you the major product. But if you're curious, when you're more likely gonna have an E2 reaction, it's usually if it's heated. So if there's heating, you're more likely gonna get an E2 reaction. Tertiary is a bit simpler, more likely gonna give you a SN1 or E1 reaction at the very least. And it will also undergo E2. So if it reacts with a strong base, you go with an E2 reaction. Otherwise, it's either SN1 or E1. So how do you know if SN1 or E1 will occur? Heating. If there is heating, we go with elimination always. If it's no heat, it typically prefers SN1 and E1. Bulky base determines whether you will follow side sev or anti-side sev. If it's no, you go with side sev. If it's yes, you go with anti-side sev. Always. We'll be moving on to a short practice of our reactions. So number 1, we have this. First question, what kind of alkyl halide is this? It's primary. Is this a strong nucleophile? Most likely, yeah. Because you're gonna have that. And then, so this would attack the central carbon and will give you this. So essentially, we'd say this is SN2. Next, we have ethyl oxide. Ethyl oxide is a strong base, but as you notice, this is a primary alkyl halide. So the ethyl oxide will attack the central carbon, which would give you, interestingly, an ether. So this is also an SN2 reaction. So next, a third butyl oxide molecule, bulky. It's a bulky base. So anything with third butyl, it's bulky. So what happens is that instead of having SN2, you'd want to go with E2 reaction. So this would attack the beta hydrogen, which will give you this alkene. So E2. If you look at this, we have a tertiary alkyl halide. So 1, 2, 3, tertiary for an E2 reaction. So what happens is that it would attack one of the beta hydrogen. Doesn't matter which one because it's symmetric anyway. And afterwards, it would form another bond and then it will cause the BRT. So you get this molecule. E2. So now we have our next question. We're given R2 bromobutane and hydroxide ion. So interestingly, we're not given a structure anymore, but instead we're given a name. So we should be able to convert this into structure form. So it's butane, and then the bromide ion is connected to the second carbon, and because it's R, we'd say this is our molecule. So to double check, 1, 2, 3 in terms of what is the priority group, and since we have that, we know this is R. It's connected. It's gonna be reacted with a strong base, so we are expecting E2 reaction rather to occur. So it would wanna attack the beta hydrogen, namely these ones. We have two options. Because periplanarity, So if it's periplanarity, it wants to attack the bottom. So the first option is the strong base will attack the beta hydrogen here. So this is our alpha, this is our beta. And what happens is that the double bond will form. So one of our products will look like this because it will cause one of the bromide ion to leave. So our other possible product is, what if the hydroxide ion attack the other hydrogen at the end, and we form a double bond here. So in this case, we have this. So these are the two products that we can have, particularly because both are connected to our groups. So both are equally substituted, so hence both are likely the major products. So now we have our last problem today, and we are given a cyclohexane with some substituents, and we also have a strong base, ethyl oxide. So we already know that most likely what's going to take place is an E2 reaction, especially since the halogen is connected to two R groups, so it's not primary, it's more secondary. So what I usually do here, it's easier to draw it in chair conformation first format so that we can easily visualize it. So Cl and the C6H5 are both in the same side, so they're both bottom. And then the methyl group, it's up here. So we have potential hydrogen here, then here. The ethyl oxide will then either attack this or this. So to better understand what occurs, we can draw both products. So one product would look like this. So if it attacks this hydrogen first, it'll form a double bond here. And then we have C6H5 and methyl group. So that's one of the product. And if this hydrogen gets attacked, it will form a double bond here. And then remove, of course, in both cases, the Cl group will be removed. So now we'll have the double bond here, which leaves us with a question: which would be the major product? Well, in this case, this would be the more major product because it's more substituted. So that's it for our topic for today. I hope that you have learned more about how to predict SN1, SN2, E1, and E2 reactions. For any questions, you may send an email to the chen.acads hub, to my email, or reach out the chen.acads hub Facebook page, because more updates will surely be placed there for other tutorials and other programs hosted by the Academics Committee of Chen. Once again, I'm Eliza Tan, and thank you for listening.